Hello and welcome to part 3 of coding Llama from scratch using PyTorch. In our previous video, we covered all the different attention mechanisms from multi-headed attention, multi-query attention, and grouped query attention. Additionally, we implemented all of these mechanisms or attention mechanisms into our 100 million parameter model. And if you haven't checked that out, I'll put the link of the video in the description below with the code. So let's move on to today. Today, we are going to focus on training our 100 million parameter model on the code parrot dataset so that we can generate code using our 100 million parameter model. Additionally, we will learn a few interesting concepts like k-value cache or key cache. We will learn about rotary positioning embeddings, which help our model have larger context windows. We're going to learn about the Hugginface Trainer and pre-trained model classes. They're going to help us make the training easier. And finally, we're going to create a generate function that's going to help us generate the outputs using this model. Since our model is an autoregressive model, meaning it outputs one word at a time, we need a special function to be able to continuously generate our outputs. So let's get started. All right, then let's do a quick recap of the work we did in our previous video. Precisely, we implemented an alternative, a better alternative to multi-headed attention, which was multi-query attention. And if you wanted to visualize these, I have the image here. So initially we had our multi-headed attention where every query matched with every key and values. And we went on to build the multi-query attention where we had a single pair of keys and values that match with multiple queries, right? We also implemented grouped query attention where we have pairs of keys and values that match with n queries. So it's kind of in-between method that takes the best of both worlds. Now, here is the code, and as I said last time, we are creating this using lists, and there's a lot of for loops within the way we were implemented. This is not the most optimal way of implementing this algorithm. It's just a way that's easier for you to understand how these things work underneath. So you can check out the GitHub repo that I will post below where you can find all of this code. Now, the problem with these is that because of the loops and the way we are creating, the algorithm is quite slow. So here's an example. This is a picture taken from Sebastian Raschka's Twitter. Sebastian is an expert when it comes to these things, and he has a new book coming out where he details how to build large language models from scratch. So check that out, and I'll put the Twitter on the link in the description below. And you can see here where the normal multi-headed attention, right, takes around 800 milliseconds. If you then change your implementation where instead of creating these using these loops, you basically create a single linear layer that you're then gonna separate into 3. You're gonna just project once and get your keys, queries, and values. It goes down to 290 milliseconds. Then if you separate those 3 now, you can get further down into 250 milliseconds. And an even better implementation of that is this multi-attention by PyTorch, where instead of you calculating your attention the way we were doing previously, you use PyTorch's new functional scale.product attention that gets you down all the way to 91 milliseconds. So you can improve your code from using loops to just using linear projections to make things better and using the tensors themselves to replicate or create new values. So now let's see how we can implement these, because over the weekend I was working on this and I implemented a more sophisticated way of doing grouped query attention. So let's go over it. So the code is pretty much the same. Actually, let me connect using a GPU now because we're gonna need that if we're gonna train this. So let's accept. Okay, we are connecting. Oh, we don't have a GPU right now. Okay, so we have no GPUs available via Colab right now, but I can show you the gist of it. So first, we just are going to install Accelerate Transformers with PyTorch, datasets from Hugginface and Hugginface Hub. Then we're just going to define these. Previously, we're just this is a function to count the parameters of the model, and this one is going to help us not to overflow the memory of the machine. So if there's something we're not using, this will be able to pretty much remove those from memory. Then we're here just going to import our libraries. A few things changed from previously. Previously, we were defining the configuration of the model as we went, like as we go. So we had the number of layers as a single variable. So one thing that I really like about transformers from Hugging Face is that you can define a pre-trained configuration where you can inherit from this class. And what you can do is pretty much define the configuration of your model. What is the vocab size? How many layers does it have? How many keys and values, heads does it have? What is the hidden activation and so on? So a few things to notice from our model. We are using a much larger hidden size from 768 to 1024. Also, we are having a bit smaller intermediate size of 2048. We have 6 hidden layers, 16 attention heads, and 2 keys and values. So you take that 16, if you divide those by 2, we have those 2 groups that are matched with the keys and values. So we only have 2 keys and values that match with 16 queries. So this is grouped query attention. We are using CLU or as our hidden activation, and our model has a context size of 2048. So you'll be able to see how we can expand the context size after training because of the way we structure things now. Here's just an initialization range for our weights. Since we are using root mean squared normalization, we have also defined that. We are not using cache at the moment. We don't have a pet token ID. And we also define rope theta and a few other configurations. You can read through them. And the model type is Llama because we are basically implementing Llama right now. There we go. Once we define those, previously here we had the code to implement multi-headed attention, but I changed a few things. First things first, we have here the way to cache our mask, and we will talk about the mask in a few. We also have this function to repeat keys and values. Since we now have only 2 pairs of keys and values that we are computing, we need a way to copy those so that we'll be able to multiply with a 16. There are still 2, but this helps us do matrix multiplication faster. And then we also have rotary positional embeddings with KV cache or keys and values cache. So let me explain a little bit about these two. First is KV cache or key value cache. Why is this important? So when you're doing inference, when you're training the model, this is not as important, but it's super important when you're doing inference. What happens is every time we pass an input through the model, we are calculating keys and values and queries from scratch. But the problem is, if you look at the input, especially when we are generating these autoregressively, is that we are recomputing K and V for pretty much the same values except the last one, except the new one. So one way to speed up inference is to cache these two values here. So the keys and values, so tensors. We cache them, and whenever there's a new input, we just pretty much concatenate this new tensor to the end of the cache. That way we don't have to recompute these from scratch, and we can just pass on the new query, and we can get our results. This can speed up inference by a lot. An example of this, I don't know if you heard about VLLM or TJI. Most of these inference frameworks do this. So if you cache the keys and values in your memory, let's say your GPU memory, you're gonna be able to generate outputs faster because you're not redoing computation from scratch. So that's KV cache. Another one is Rotary positional embeddings. These are super important because compared to what we were doing previously, which was fixed positional embeddings, where we had an embedding matrix and we added that to our original embedding matrix so that we can pass on some information about the position of a particular item. When it comes to rotary position embeddings, we actually can use angles to tell the model where does a particular item or input stands in position wise. This is important because if you look at the normal fixed position embeddings or sinusoidal position embeddings, the angles you get as you increase your input, let's say you trained your model to have a context size of 10. If you pass on an 11th item, your model is going to output garbage basically. So this fixes it by creating an angle that encodes the position of the input. And if let's say this is just a visualization in the 2D plane, if you were to see this in 3D, let's say you have more than 2 dimensions, what we do is that we take the first side of the tensor and the second side of the tensor, and we rotate them by 90 degrees. So the first side is actually kept fixed. The second side is rotated by 90 degrees. So this gives us positional information, and we can extend these positions even after pre-training, which is pretty good. There's a really great video that explains this in depth, and I will link them in the description below. It's actually 2 videos if you really want to watch them, and I also have a really nice blog post about this. So now let's go into the implementation one by one. So rotary positional embeddings, what does it take? It takes the dimension, meaning our hidden dimension, number of positions. In this case, we have a context size of 2048. Our base, this is going to help us generate our theta value. That also helps us generate our costs and sine waves. And then we have the device. This is just going to help us make sure that the tensors are in the same device. So let's say if I'm using GPUs or CPU, it's going to be helpful. And scaling factor. This comes into play later. Let's say after training, we can increase the scaling factor. And this is going to help us, let's say, double, for example, the context window of our model. So from there, this is just the formula for theta. It's a very simple formula. It's like 1 over our base, which is 10,000 over our position. Max positions, right? Max positions divided by our dimension. It's a very simple formula. I will link to an article that has these built in. Then after we define these, we are just gonna set the initial cos and sin values, or cosine and sine values, by just passing in our default values here. And what is this going to do is that it's going to first get the positions of our maximum context window, gonna divide this by the scaling factor, and then we are going to get the frequencies and concatenate both of them to get the cosine and sine values, and we're gonna pass this into the buffer here. What this is going to do is that this is gonna set them in on the GPU in such a way that we are not gonna do back propagation on these tensors. And in our forward, if our current sequence length is bigger than the max sequence length, we are gonna add more, we're gonna create new sine and cosine values. And what we do here is that we just get the first everything up to sequence length when we retrieve these values here. And in our apply rope function here, we are just, it's a very simple function. So we get our sine and cosine values using the position IDs. We unsqueeze these values so that we can get, let's say if we get a matrix that's like 5 by 5, when we do unsqueeze on the dimension 1, we're just adding one dimension in the middle. This is gonna help us later when we are gonna do the operation. And here, what we are doing is that we are getting the first half of the matrix and the second half. And what we do is that we take the second half, and when we do this negation here, what basically we are doing is rotating this second half by 90 degrees. And when we concatenate them back, we now have a rotated matrix. And this rotated matrix is pretty much multiplication of, and with this rotated matrix, we're going to calculate our rope value. So the operation is as follows. We take our x, we multiply by the cosine, and we add that to the rotated matrix times the sine wave. So this is how you pretty much get your rope values. And for you to visualize these, you can just imagine that it's going to look something like this in the 2D plane. Now, and we already did this, we did this there when we rotated the matrix. So that's a rope, and KV cache is a very simple one. We instantiate a K and V values or tensors with zeros initially, right? And when we call these, we pass on our positions. So we take the number of positions we have, which is basically a tensor. And we also take this K and V values, and what we do is that we copy them into K and V here. And we return those two, right? So now we can reuse, since this is a copy, this is a copy of an existing so now we can reuse existing values of K and V. So if we pass on new values, we are just copying the new values, and that's it. We are just storing them in this K and V. But for training, this is not important, so we will skip K and V altogether, right? K value cache altogether right now. So for training, this is not important, so we're gonna skip it. I just kept it here so that you can see and understand how it works. We can use this at inference time. So after we finish training our different model sizes, the 100 million, the 400 million, and the 250 million parameter models, we are gonna add this to our model code when we upload it to Hugginface, so that you can benefit from key value cache. But right now, we don't need it. All right. The idea of key value cache, you can see here, it's a very simple one in practice. So let's say we have two sequences right? Two samples, each with two characters, you can imagine, or two words. And the dimension, the dimension we are embedding is 3. So once we have our K cache, which is basically a bunch of zeros that has the same shape as K, we can now take our positional embeddings, which is just gonna be the second element of K, which is in this case 3. But if we had our normal input, which is going to be B by a number of heads, by sequence length, by head dimension, in this case, we would have gotten sequence length. But in this case, we're just getting the head dimension. And that's going to be our position IDs. This is going to tell the model where, or the system, where the inputs are positioned. When we do K cache index copy of position 2, right? And then we pass on the position IDs and K. What we are doing, since you saw that initially it was just zeros, we are just basically copying K. And you can see now that K cache now contains K. And that's basically how key value cache would work. And it's the same, it's pretty much the same code one-to-one. Here's just a smaller representation. You can add, for example, as an exercise, n heads. N heads, in this case, you can say this would be 2, and see how would that work. All right. Now, let's go into our attention mechanism. It has changed a lot. So before we were passing on the arguments one by one, but now we just pass in the configuration. This configuration already has our hidden dimension. We pass on our hidden dimension, number of attention heads, which is going to be n heads, number of key value heads, which is going to be nkv heads, and the head dimension, which is basically dividing the hidden size by number of heads. And whether we use bias here in our linear layers, right? After we have these, we get the number of repetitions. So you know that when we're doing grouped query attention, we have, let's say, 2 pairs of Ks and Vs there are for n queries. Because of that, computationally, it's more efficient if we just copy those or repeat the existing keys and values and multiply them using matrix multiplication. So here we're just finding out how many times do we have to repeat to match the keys and values with the heads. And then we have our query projection. So what we do now, instead of repeating this in a for loop, we start with our hidden dimension and we project these to n heads times head dimension, right? So we will get queries by n heads, right? And then in our keys and values, we embed this into the head dimension times Ks and Vs. So in our case, we have about 16 heads, and each head has 2 keys and values, right? And finally, our output projection in this case is going to be n heads, right, times head dimension into hidden space. And here we just define our rotary positional embedding. And these are just the arguments we passed on before. And we also have our KV cache here that we're not going to use, but it's here just to show you how this would work. Then in our forward pass, we pass on our input, our mask, and our position IDs. So the position information about the input. And what we do here initially, we just take the shape of the input, in this case, the batch dimension, the sequence length, and the embed dimension. This we are going to use later to shape our tensors. So when we do the forward in our queries, keys, and values, we now have these, and we can reshape them so that they are batch size by sequence length by number of heads. So instead of being n heads times head dimension, now we can create a new tensor with dot view that has n heads, comma head dimension. So basically how this looks like, it looks something like, let me just copy these. It's gonna be easier. So it looks like batch sequence length, n heads, right? N heads. And finally, it's gonna be, instead of embed dimension, it's gonna be head dimension. And the same thing can be done here, but the difference here is instead of n heads, we have n kv heads. And finally, the same thing goes also to values. So now we have a tensor that's of these two different shapes. We can now get our rotary position embeddings by passing on the values and the size of the sequence length of keys. That's going to give us our cos and sine values that we can later use to apply rotary position embeddings or rope to the queries and keys, right? So once we have these values, these tensors roped, we can now repeat them. Or alternatively, if we were doing inference, this is where we would do the key value cache. We would cache the new values so that they can be used later on. So in this case, we are not doing key value cache, but this would be the place where you would cache the keys and values. So here we just repeat these. The repeat function I already defined earlier. We just pass the keys and however many times we want to repeat, and the same thing for values, and we have our new keys and values that are repeated. And following that, in some cases you might, if you let's say if you're using GPUs, you might want to set these to contiguous, because if it's not contiguous, it might give you an error. So here I just define these. It's just a normal condition. And then I have this function here that calculates my dot product attention or scale dot product attention. And it's as before, we calculate our scale, but the difference is instead of implementing these by hand, we are using torch NN functional scale dot product attention, passing in our keys, queries and values, and passing in is casual because we are training an autoregressive model, so this is important. And then we just transpose these to match our input here. And finally, we pass that to our output projection layer. Here's just a normal reshape because we get back B by T by N heads by head dimension. And we actually just want to morph these last two into hidden dimension so that we can process it here. And that's basically all you need to know that changed in our baby llama attention. So now let's run it. Okay, so when we run it, I'm not gonna load this model, I just wanna load the configuration. When we run it, it should give us the same shape as before. And here's how it looks like. So we have 1024 input, output is 1024 for our query projection. And here we have 128, right? And the same thing for values. But when we merge all of these, again, it's gonna be 124 and you're gonna get the output as 124. There we go. And this attention mechanism has about 2 million parameters. Then we define our multi-layer perceptron, right? For our Llama model. And how this is implemented for the Llama model, it's just basically 2 linear layers with a SILU activation and an output projection layer. And in the original one, they used dropout, and also in the original one, they add another layer, like a third layer. And the way we do this is by calculating the first linear layer, the second linear layer. After we get that, we pass on the output of the first layer, linear layer, into an activation. We multiply that by the second layer output, and we pass on to a output projection. That's gonna give us the same kind of shape of output that as we had before, and this has about 6.3 million parameters. Now we go into our block. This block, what it does is that it compiles. We now have the attention mechanism, the multi-layer perceptron, and we have normalization. So the way we are going to do normalization is doing basically a root mean squared layer normalization. So the way we do this is by squaring all of our values and calculating the mean to get the variance. Then we take the initial values, right, and multiply by the square root of the variance plus the variance epsilon, right? And we then multiply that by the weight. This is a parameter we optimize, so we multiply that by the weight, and then we have our root mean squared normalization. And we do that 2 times. We do that to our input and our output. The way it works is by you first take the input, you normalize that input, right? Then you pass it on to your attention layer. You're gonna get a residual value there. We then take again the initial input and we pass on that, and we add it to the residual value. And again, we get another residual value by taking our intermediate value here, intermediate state, passing on to our post normalization, and then passing it to our multi-layer perceptron. And finally, just adding both of them, and that's our output. Basically, you can think about these as just skip connections, where we have our first skip connection that adds to the original input. Then we have our second skip connection that adds to the previous stage here, which was this intermediate value here. Now, this block has about 8.6 million parameters. And now we go on to the main character of the show, which is our model. And the way we define this model is pretty simple. We initialize our hidden dimension and our vocab size. That's gonna help us define our embedding. So you just create an NN embedding. Then we're just gonna iterate over and create these blocks iteratively. So we're gonna have 6 blocks, right? And then finally, before the output, we are gonna have our normalization again. If you look at the original paper, we had this normalization after the multi-headed attention, and we also have this after our MLP before we calculate our logits. So basically, we are creating this block, and after the block, we are also adding these normalization here, right? So we are gonna run this. And now the way this is going to work is we embed our input. We take our input here, we create embeddings, so token embeddings of the input. Then if the position IDs are not passed, we create one by taking the sequence length and doing a torch arrange. So this is gonna create a vector of the size of sequence length. And we just iteratively pass the position IDs, the mask, and the input through our blocks. And then after that, we pretty much pass it to our normalization layer. Now, here's the important part. To be able to leverage the Hugginface abstractions or existing abstractions, I found it much easier to just port our model into the Hugginface format. The way this works is we could just pass on our normal PyTorch NNN module model, but I found it easier to just use the existing abstractions they have. Just makes things much easier. So here we defined a pre-trained model. This pre-trained model has a few properties. So it takes a configuration. It has the base prefix model. This is just Hugging Face specific. Supports gradient checkpointing. I set that to true because I want to be able to do the propagation every few steps, not every step. And then it also skips past keys and values. So basically this is key value cache. Hugging Face already does this for you under the hood. So you might want to define these to false so that they don't get passed during training. And then we are going to initialize the weights. The way we initialize the weights is we're going to take a normal distribution. And then within this normal distribution, remember the range we defined earlier, we're going to take that as our standard deviation. And we're going to do that for both our linear layers and embedding layers. And that's pretty much it. So after that, we can inherit that so that we can define our model where it just creates a baby llama model as we did before, sets the vocab size so that we can then finally create our LM head. This is going to give us the logits. And then we're going to use those logits to decipher the output of the model. So what this does is that it takes a hidden size, which is going to be the output of the model, and projects that into the vocab size space. So vocab size, we are talking about 32 tokens. So it's going to create an embedding of 32,000, sorry. And we also set the bias, in this case is false. And it's very simple, straightforward. We get the outputs of the model and we pass that into our LM head. We get the logits, we set them to float. One thing that you can do when you're using the Hugging Face pre-trained, when you inherit from the Hugging Face pre-trained model class, is that you can define, if the labels are not present, you can shift both the logits and the inputs. Since we are trying to do next token prediction, we take the input and we're trying to predict what word comes next. We want to shift the labels and the output so that we can predict those. So the first element of the labels and the last element of the token are not as important to calculate the loss. So that's why we shift them. And after we shift them, we calculate the cross entropy loss. And then we are going to set this loss value. But in case the labels are present, we set the loss value. Otherwise, it remains none. And then another nice thing about using the Hugging Face pre-trained model is that they have this class called casual LM output with past. So you can use this class to pretty much pass your key value cache. You can use it to pass on a bunch of things. I guess the list goes on. So here's just the logits, hidden states, attentions, and so on. But in our case, we are just gonna pass the loss and the logits. This is gonna structure everything beautifully. So when I instantiate this model, I said to CUDA, it should be CPU. There we go. It was CPU before. And I cannot use torch.device for some reason because Hugging Face Trainer tries to serialize that, and that just gives me problems. So that's why I'm kind of creating it this way. I could run the model, but basically what you would get if you pass the inputs and the labels as well, you get a loss value, which is great. In this case, it's 10. And you also get the logits. What you can do with the logits then is pretty much calculate, find out what the model predicted. And we'll go through that in a second. Following that, we can just see how many parameters. And this is a 117 million parameter model, which is great. Now let's move on to the dataset. I use the CodeParrot dataset, and I take about 1% because this dataset is too big, and Colab seems to die out quicker. Like the memory is low. It takes more than 12 gigabytes of RAM to be able to process this dataset. So I take a small subset of this dataset, which is about 1%. But you'll see we really get good results or decent results with 1%. Of course, if you really want to train this seriously, you might want to consider taking the full data set and training it training it on the whole data set. But in this, just for demonstration purposes, I'm gonna take just 1%. And you can see here it's a big data set. So while it loads, we can continue. After we get the data set, we're just gonna see that this data set contains repo name, path, copies, size, content. And we are interested in the content of that repo, which is the code we're gonna use to train this model. We set our Hugginface hub token. This is gonna allow us to download the Llama 2.7b tokenizer. This is gonna help us tokenize our data set. And in this case, we are using this tokenizer because it's already an existing tokenizer and we are trying to replicate the Llama 2 model. So we can just take this tokenizer and reuse it instead of creating our own from scratch. So I just set the add end of sequence token because this tokenizer by default does not include the end of sequence token. So if you pass on this variable here, you'll be able to get the end of sequence token when you tokenize any text. So here's an example. Hi, I'm Prince, and this tokenizes to pretty much this one. And I guess and the true tokenizer it's using under the hood is sentence piece. So you might want to check out sentence piece to understand how it works. Now, another thing that I have to mention is that since you don't have a pet token, you need to set it. For generation, you can set the pet token as end of sequence token. But for training, I found that just using the unknown token as my pet token already helps because I don't use this token during training. And here we're just gonna tokenize a sample of our data set, right? We're gonna add the padding, we are gonna truncate. So if the sequence is bigger than 2048, which is our context size, we're gonna add the end of sequence token, and then we're gonna take the overflow and put it onto the next sample. The same thing. So yeah, basically that's it. We set the max context length. In this case, of course, we set it. I just set it to 10 just for demonstration purposes. But our true context length is 2048. Here we set the data collator. What this does is that it does exactly as it suggests. It creates chunks of inputs and labels for the data set for particularly the language modeling task, which is basically next token prediction. And we pass on the tokenizer, and we are not doing masked training, so we can set this to false, and we want to return PyTorch tensors. And here's a sample of how the data would look like. You can see 1 and 2, these are just the start and end of sequence token, the S and bar S token, right? And these are the inputs, the attention mask, right? Whether this belong to the same group or not. Is there any overflow? No, there isn't. And what are the labels? So the labels are pretty much the input. And since we already shift this inside the model, it's not really a big deal. And we can pass on a sample through our model just to see how it would work. We pass on the inputs and labels, and we get 10 again. It's not really good. And you can see here when we decode the output, this decodes to M. It's really not doing anything good. Like it's not really predicting good because the loss is too high. Now, we are going to then instead tokenize the entire data set by creating a function that creates the tokenizer that replicates what we just did with the tokenizer. And we're going to map that to our data set. What this is going to do is that it's going to create a data set of just input IDs, which are going to be the tokens and labels. After we do that, we can pretty much start the training. In this case, I will set the max steps. These are gonna be 2000, and here logging steps, basically after how many steps do I want to see the loss and the eval loss. It's 10. I want to accumulate the gradient every 2 samples or batch of 2, and the batch size that I want when I'm training is 32. The warm-up, rate decay, these are just the normal default parameters you want to set when training this model. You can also check the paper for the full list of parameters you want to set. Here I'm just setting a few just to show you how this would work. Then we can now use the trainer. The way we use the trainer is just passing on the model, the tokenizer, the arguments, which are these one here. We pass on the data collator and the tokenized dataset. So the data collator is going to create the batches that we need internally. And after we train the model, here's an example that I was training yesterday because it was about to take almost 3 hours. Actually, it started at 3 hours. I waited about 40 minutes for this. So you can see the model starts training, and we can see that the loss is going down from 9 to 6 to 5 to 4. It hovers around 4 and 5, and then goes down to 3. At the end of all of this, around 1500 steps, you can see it was in the low 3s. And I thought, why not stop here and see how the model performs? So now I instantiate the tokenizer again, but without the add end of sequence token, because I don't want to add the end of sequence token to my input. I want the model to complete and then itself to predict the end of sequence token. And now I can set the pad token as the end of sequence token. And here's the generate function. Basically, we create the tokens. In this case, my input is import numpy. It's just gonna return the PyTorch tensors using the GPU. In this case, I was using GPU. I'm gonna get the input IDs. I'm gonna set the temperature of the model to 1. And top K and top P, I'm gonna set them to none. These are just gonna help you help the model sample from different distributions. And I'm not gonna focus on that here right now. So I'm gonna generate 10 tokens by iterating 10 times. The first time I'm just gonna pass on the model, the input ID to the model. I'm gonna get the logits of the last item. So the last item in this tensor. I'm gonna divide the logits by 1. In this case, it's just gonna be the same value. If I want the model to be a bit crazier, I can set this value a bit lower in the, let's say 0.7, 0.5. And then I'm gonna just pass the logits to a softmax so that I can get the distribution, probability distribution, and then I'm just gonna get what is the ID of that token. So which value in this 32,000 vocab size is the most likely. And after that, I'm gonna append this token ID to the original input IDs on the last dimension. So I'm just gonna take this new word, add it, and then I'm gonna repeat this cycle 10 times. And finally, I'm just gonna decode this value. And you can see here that after I run that, I get here in the generated text, import numpy as NP, and then it also imports matplotlib as PLT, which is pretty good. Actually, these are quite likely to occur together if you do data science. You most likely import matplotlib alongside numpy, pandas, and so on. So for a model that trained just a little bit and it only has 100 million parameters, this one is doing really good. And then after I finish this, I can just do trainer push to hub, and I created this model here that you can download and check it out. So yeah, that's it. Check out the code in the description below and let me know if you have any questions. On the next one, I'm gonna announce soon what we're gonna be doing. But I guess one thing to think about is to extend the training of this model, the 100 million, and also start working on the 400 million and 250 million parameter model. So that's it for today. Thank you. Bye-bye.